Means. In this section, we will discuss measures of the size of the difference between means. We begin with the case in which the dependent variable is measured on a scale that is intrinsically meaningful. We then discuss measures when a scale is not intrinsically meaningful and the use of standardized measures of these measures. Finally, we discuss some interpretational issues in measuring effect size. When the units of a measurement scale are meaningful in their own right, then the difference between means is often a good and easily interpretable measure of effect size. For example, a study done by Holbrook, Crowther, Lauder, Cheng, and Kingen conducted in 2000 investigated the effectiveness of benzodiazepine for the treatment of insomnia. These researchers found that compared to a placebo, this drug increased total sleep duration by a mean of 61.8 minutes. This difference in means shows clearly the degree to which the drug is effective. It is important to note that the drug was found to sometimes have adverse side effects. When the dependent variable is measured on a ratio scale, then it is often informative to consider the proportional difference between means in addition to the absolute difference. For example, if in the Holbrook et al. Study, the mean total sleep time for the placebo group was 120 minutes, then the 61.8-minute increase would represent a 51% increase in sleep time. On the other hand, if the mean sleep time for the placebo were 420 minutes, then the 61.8-minute increase would represent a 15% increase in sleep time. When the scale of a dependent variable is not inherently meaningful, it is common to consider the difference between means in standardized units. That is, effect size is measured in terms of how the number of standard deviations the means differ by. Two commonly used measures are Hedges G and Cohen's D. Both of these measures consist of the difference between means divided by the standard deviation. They differ only in that Hedges G uses the version of the standard deviation formula in which you divide by n-1, whereas Cohen's D uses the version in which you divide by n. Standardized measures such as Cohen's D and Hedges D have the advantage that they are scale-free. That is, since the dependent variable is standardized, the original units are placed by standardized units and are interpretable even if the original scales unit do not have a clear meaning. Consider the animal research case study. The mean for women was 5.353, the mean for men was 3.882, and MSE was 2.864. Therefore, Hedges G is 0.87. It is more meaningful to say that the means were 0.87 standard deviations apart than 1.47 scale units apart, since the scale units are not well defined. It is natural to ask what constitutes a large effect. Although there is no objective answer to this question, the guidelines suggest by Cohen in 1988 that an effect size of 0.2 is a small effect, an effect size of 0.5 is a medium effect, and an effect size of 0.8 is large effect have been widely adopted. Based on these guidelines, the effect size of 0.87 is a large effect. It should be noted, however, that these guidelines are somewhat arbitrary and have not been universally accepted. It is important to realize that the importance of an effect depends on the context. For example, a small effect can make a big difference if only extreme observations are of interest. Consider a situation in which a test is used to select students for a highly selective program. Assume that there are two types of students, red and blue, and the mean for the red students is 52, and the mean for the blue students is 50. Both distributions are normal, and the standard deviation for each distribution is 10. The difference in mean is therefore only 0.2 standard deviations and would generally be considered to be a small difference. Now assume that the only student who scored 70 or higher would be selected for the program. Would there be a big difference between the proportion of blue and red students who would be able to be accepted into the program? It turns out that the proportion of red students who qualify is 0.036. The proportion for the blue students is 0.023. Although this difference is small in absolute terms, the ratio of red to blue students who qualify is 1.6 to 1. This means that if 100 students were to be accepted and if equal number of randomly selected red and blue students applied, 62% of the red and 38% of the blue would be accepted. In most contexts, this would be considered an important difference. When the effect size is measured in standard deviation units, as it is for Hedges G and Cohen's D, it is important to recognize that the variability in the subjects has a large influence on the effect size measure. Therefore, if two experiments both compared the same treatment to a control, but the subjects were much more homogeneous in experiment 1 than in experiment 2, then a standardized effect size measure would be much larger in the former experiment than in the latter. Consider two hypothetical experiments on the effect of an exercise program on blood pressure. Assume that the mean effect on systolic blood pressure of the program is 10, and that due to differences in the subject population sampled in the two experiments, the standard deviation was 20 in experiment 1 and 30 in experiment 2. Under these conditions, the standardized measure of effect size would be 0.5 in experiment 1 and 0.33 in experiment 2. This standardized difference in effect size occurs even though the effectiveness of the treatment is exactly the same in the two experiments.